Hello everyone, I'm Dragon and welcome to today's explainer. We're going to be jumping right into the invisible, magical world of hot and cold today. Now obviously, being a red dragon, I know a little something about getting things warmed up. But even I need solid science to actually understand the mechanics of what's happening around me. So let's unlock some fiery knowledge. Okay, let's dive straight into this. Heat and temperature. We toss these words around in everyday conversation all the time. Right? You step outside and say, wow, the heat is intense today. Or maybe your doctor says, your body temperature is a bit high. But here's the central mystery we're tackling today. Do those two words actually mean the exact same thing? Just kind of keep that question in the back of your mind as we go, because the answer might actually surprise you. Let's kick things off with temperature. Imagine you've got two chalices in front of you, one full of fire, one full of ice. You'd probably just call them hotter or colder, but honestly, in science, just saying hotter gets incredibly confusing really fast. We need specifics. So scientists use numbers to measure the exact degree of hotness. That measurement, that's what we call temperature. And to make sure everyone on the planet is speaking the exact same scientific language, we measure this using a standard unit called degrees Celsius. Now, my claws can usually tell me pretty quickly if something is boiling or freezing, but for exact numbers, we rely on thermometers. And there are quite a few specialized tools for the job. First step, the digital thermometer. It looks a bit like a tiny magic wand, and it's absolutely perfect for taking a quick body temperature reading. Then we have the infrared thermometer. This one is super cool because it measures the surface temperature of solids and liquids from a distance, no touching required. Next is the classic laboratory thermometer, specially designed for dipping into potions, liquids, and gases. Oh, and for some high-tech magic, we use a data logger. It's essentially a digital tablet connected straight to a sensor, and it tracks temperature readings continuously over time. Out of all those tools, the laboratory thermometer is totally essential for everyday experiments. But here's the catch. Reading it accurately actually takes a specific technique. You can't just glance at it. So how exactly do we read a lab thermometer like a true science wizard? Well, let's break down the pro tips. It literally comes down to 3 absolutely crucial steps. Step 1, you've got to immerse the bulb. That's the little bottom tip of the thermometer. It has to be completely covered by the liquid you're testing. Step 2, just wait. You'll see the red liquid inside that glass tube start to move. You need to be patient and wait for it to completely stop rising or falling. And step 3, which is probably the most important part of the whole process, read it exactly at eye level. Actually, let me explain why that last step matters so much. Okay, so here's the eye level secret. When you look really closely inside that super thin glass tube, the surface of the red liquid isn't flat. It actually curves slightly. It's kind of like a tiny little bowl. For a truly accurate scientific reading, you have to position your head so your eye is completely level with the very bottom of that curve. If you look down at it from above or peek up at it from below, you're going to skew your data and get the wrong number. All right, so we've got temperature and how to measure it locked down. But remember that mystery from the very beginning? What about heat? Well, here is the big reveal. Heat is actually a form of invisible energy. Just like light is a form of energy, heat is too. And this energy has a superpower. It physically causes the temperature of an object to change. When an object gains this heat energy, its temperature goes up. When it loses that heat energy, the temperature goes down. And this perfectly illustrates the ultimate difference between the two concepts. Heat is the active force. It's the energy that actually causes the changes to happen. Temperature, on the flip side, is just the measurement. It's a property of that object at one specific moment in time. Basically, heat is the reason why the temperature changes. They're a team, for sure, but they are absolutely not the same thing. Now that we know heat is essentially energy on the move, we need to understand how it travels. I like to call this the golden rule of dragonfire. Ready for it? Heat always flows from a hotter object to a colder object. It literally never goes the other way around on its own. The energy is always going to travel from where there is more hotness to where there is less hotness. Let's look at how this golden rule works in the real world. Imagine it's a super chilly morning, and you've got a bottle of milk straight from the fridge. It's way too cold to drink. If you place that cold bottle into a basin of hot water, what happens? Well, because heat always flows from hotter to colder, the hot water acts like a donor. It gives away or loses its heat energy, meaning its temperature actually decreases. At the exact same time that cold milk acts as the receiver, it gains that exact same heat energy, so its temperature increases until it's perfectly warm. We can actually map this invisible process out over time using a cooling curve.
If you leave a beaker of really hot water just sitting on a table, right at 0 minutes, our golden rule kicks in. Because the water is hotter than the air in the room, it immediately starts losing heat to its surroundings. As the minutes tick by, the curve drops lower and lower. But then, notice how it flattens out? Why does it do that? Because the water finally reached room temperature. Once the water and the room are at the exact same temperature, the heat transfer completely stops.
And we see the exact opposite happen with a heating curve. If you leave a beaker of icy cold water on that very same table, the heat energy flows from the hotter room directly into the cold water. The water gains heat, and the curve climbs steadily upwards as its temperature increases. But just like before, this whole warming process stops the very second the water's temperature matches the room's temperature. We've covered some genuinely fantastic ground in this explainer today. We learned that temperature is the number we measure in degrees Celsius, while heat is the actual invisible energy making that number jump up and down. And we mastered the golden rule. Heat is always on the move, flowing from hot to cold. But I want to leave you with a little something to ponder. Think about this later today. If heat always flows from hot to cold, when you leave a bowl of steaming hot soup on the table and it eventually cools down, where exactly did all that invisible heat energy go? Keep exploring, keep asking questions, and I'll catch you in the next explainer.